All right, let's get started for today. A couple of announcements. Homework 3 games is due tonight, exceptionally, right, because of the holiday yesterday. Project 2 is due on Friday at 5 p.m. with the optional contests having its deadline Sunday at midnight. And you have something else due today if you haven't done it yet, which is the edX Panagrader User ID Consolidation Survey, which allows us to pair up both places where we have your grades. All right, back to Markov decision processes. So as a reminder, here's our kind of running example MDP. But keep in mind at the same time that MDPs can be many types. It doesn't have to be a grid world. But here we had a maze-like problem. There was the state of the agent corresponds to the location of the agent. There is a reward for taking the exit action over here of +1, a reward for the exit action over here of -1. And everywhere else, the choice of actions is to move in any of the 4 directions that north, east, southwest that might be available. If you move into a wall, it doesn't have any effect. If you decide to move in a certain direction, only 80% of the chance does it actually get executed. 20% of the time you veer off to the left or to the right. There might be something called a living reward. The idea there is that you penalize the agent for taking time to get to the goals. An MDP doesn't have to be set up with goals. This is a special kind of MDP where there's a goal state in some sense. Once you take the exit action from this state over here, you reach this done state where everything's done, nothing happens anymore. It doesn't have to be that way. But often your problems are that way, that you want to achieve a certain state. In those cases, if you want to achieve it sooner, you might want to apply a negative living reward at each time step to punish for taking too long. You can achieve the same thing with discounting. So if you discount rewards, then you'll also encourage to get the rewards, at least the positive rewards, earlier rather than later. All right, so this is our example. In terms of terminology, just like in search, we had states, we had actions, we had a successor function in search. Now it's a transition model that can be stochastic. P, S prime, given S comma A is the probability of landing in state S prime. Given you were in state S and took action A, we also write it this way as TSAS prime. With the transition from S through action A into S prime, there's a reward associated with that. So the reward function is a 3-dimensional table in general. And these rewards could be discounted where the reward at time 0, or at the first time step, is not discounted at all. At the next time step is discounted by gamma. Next time step, gamma squared, and so forth. And then there can be a start state. The quantities we've looked at are, first of all, a policy. This is what we're after, the thing we want to find when we solve an MDP. It prescribes to us for every state what the right action is. If we have the optimal policy, then that will prescribe to us what the optimal ways to act in each state. Keep in mind that there are 2 types of policies. If we have a stationary, if our utilities are stationary, then the optimal policy will also be stationary, and that policy will just prescribe an action for each state. If we have non-stationary utilities, or we have a finite horizon MDP where we know we'll only act for, let's say, 10 time steps, then the policy will prescribe an action for each state and each time step. So now it becomes a much bigger table, because once you have a non-stationary policy, it'll depend on the time step you're in. In particular, you'll index it by how many time steps are left in your MDP. All right, utility. We saw a lot about utilities 2 lectures ago. Here we assume the utility is the sum of discounted rewards. The value of a node is the expected utility, so the expected sum of discounted rewards, if you were to act optimally. Then a Q value was a slight variant on that, and was if you're in a certain state and you just took a certain action. So let's say you started in state S, you just took the action A, you land in this thing called a Q state. At that point, you're committed to your action, but the action hasn't played out yet. Some randomness will come into play here in general and decide what the next state S prime is. But right now, you're right here. The Q value of a state action pair is the expected sum of rewards with discounting if you were to act optimally from then onwards. So it doesn't assume that your action A was optimal. This might have been suboptimal, but it assumes that from then onwards, you'll be acting optimally. What is then your expected sum of rewards with discounting? All right, so V values are associated with these maximizer nodes and Q values with the chance nodes or the Q states. Let's take a look at the values here for our Gridworld MDP. So if we look at the values, we have a value of 1 over here. Why is that? The optimal thing to do is the only thing you have available to you, which is to take the exit action, and which gives you a reward of 1. Over here, 0.85. How is it 0.85? Well, roughly what's going on is the optimal thing to do is to move here and then exit. That would give you a reward of 1, but you get it only later. So due to discounting, if let's say the discount factor were 0.9, if you were to start here, move there, and exit, your reward would be 0.9 times 1. So 0.9. Still, it's not 0.9 here because it's not guaranteed that your action succeeds. There's a chance that you actually move this way or that you move that way, which means you stay in place. When that happens, you'll continue acting, and from here you would move up, and from here you would again try to move there. And if we average it out, on the average, taking into account discounting, you get an expected utility of 0.85 from that particular state. And similarly for the other states. We can also look at in detail what for each action, so for the Q states, what the values are. So we have the 0.85 still over here. It's the maximum of the 4 Q values for that state. This is the Q value for that state in action north, this state in action west, this state in action south. The value we saw is the maximum of these Q values. And let's take a look at, for example, this one over here. The Q value for moving down, 0.3. What is that encoding? It assumes that at the first time step, you take the action south. Might or might not succeed. If you're unlucky, you move off into the pit. If you're medium unlucky, you move into the wall and stay in place. If you are lucky, is that the action you want to take, you actually 80% of the time land in the square below. At that point, you act optimally. You look at the Q values here, 0.48, right over here is the highest. So you would take this action, you would move up, back into that square. If it succeeds, but there's of course a chance you move sideways. If you were to succeed and are back here, you act optimally, and that would in this case be moving north, because 0.57 is the highest, and so forth. So keep in mind when you look at these Q values, it assumes just at the current first time step that you take that action, but from then onwards, no matter where you are, you would act optimally. All right, so the terminology was V star of S is the expected utility starting in S and acting optimally, and you'd be sitting over here in the expect-max tree. The value of a Q state, state and action pair, Q star SA is the expected utility starting out having taken action A from state S and thereafter acting optimally, so it'd be sitting over here. The optimal policy, pi star of S, is the optimal action from state S. We've annotated them all onto this expect-max tree, or part of an expect-max tree, because these are effectively what they are. And we know that the main difference between what we saw in the expect-max lecture versus last lecture is that we looked at a different way of solving these problems using a dynamic programming method that allows us to solve these problems more efficiently, even for very deep trees. The flip side, of course, was that we assumed a state space that we can enumerate. So in expect-max, you might say, oh, we're only going a few steps deep, and you only need to consider the states you might actually encounter. Here we go infinitely deep, and so all states might come into play. But the algorithms we've looked at will then loop over all states, and it's assumed that we can do that. All right, so the main equation we've seen, and we'll see coming back and back in different forms, is the Bellman equation. And kind of the simplest way to think of it is that it says, first take the correct action, and from then onwards, continue to be optimal. So you decompose being optimal in being optimal now, and then continuing to be optimal. All right, so that's what expected max does, so we can map this back to expected max. V star of S is the max overall action of Q star SA, which is sitting over here. The Q equation is a little more complicated, so let's work that step by step. So Q star SA, what's the value for a chance node? Well, we get now a reward for the transition into the next state S prime. But not just a reward for the transition, we also get, at the next time onwards, we'll keep accumulating rewards, and we know that we'll be acting optimally, so from S star onwards, we'll accumulate, on the average, V star of S prime. We'll only hit state S star at the next time step. So the rewards we accumulate from S star onwards are all discounted by a factor gamma. So the value here is discounted by a factor gamma, and deeper rewards are discounted by even more, which is already encoded in V star of S prime. We don't know which state we're going to visit, so there is a sum over possible next states, and we weight each of these possible next states by the probability of landing in that next state. That's our Q star equation. You can also write it out at once, substituting this thing here in here. And a lot of people write it that way, and when you write it that way, it's often called the Bellman equation. So let's look at it in printed form. This here is the Bellman equation. Now let's make sure we fully understand what's going on here. So it's saying that the value of a state S prime, of a state S, is equal to, and then here we max over all possible actions that we have in state S, and we max over these values here, which are Q values, and they are computed by averaging over possible next states when taking that action A of the reward you get instantaneously, plus then a discount factor gamma times the expected discounted rewards from state S prime onwards if you were to act optimally. Okay, so this is the Bellman equation. And there are many equations that are similar that are often also called Bellman equations. But if you're only going to call one of them the Bellman equation, you're going to pick this one. All right. So value iteration. Yes?
If the gamma is encoded in the V star of S, then why is it needed for the first one?
Okay, so why? So let's take a closer look at what's happening underneath here. What's happening underneath here, V star of S prime is equal to an average, so an expected value, right, of the reward you'd get right away. Let's say R0, new notation, but let's just denote it this way, plus then gamma times R1 plus gamma squared R2, and so forth, till infinity, assuming you act according to the optimal policy, starting in state S prime. But now, since this is only starting one time step later, you need another gamma up front here to make it be the right thing. Because V star of S prime doesn't discount the first one, but it's coming in one time step later because S prime is sitting here. Okay, so the Bellman equations characterize what the optimal value function is, V star. So we know that this encodes the optimal value function. And any method you have to solve this set of equations, what is this? This is a set of nonlinear equations. There are capital S states, so there are capital S of these equations. There are capital S unknowns, V star for each of the states. So you have capital S equations, capital S unknowns. In principle, you could solve this. Often there will be a unique solution. We have as many equations as unknowns. It's not guaranteed, but in this case it actually is true. And whatever you use to solve this is fine, and you can then verify that you indeed found the solution. We looked at a very particular way of solving this set of equations, and we did it in a way that actually gives meaning to the intermediate results we compute. So we said, we can solve this set of equations by iterating this process over here. Vk here is the optimal value if there are only k time steps left. We assume we have Vk available, and this equation then tells us how to compute Vk plus 1. The optimal value with k plus 1 time steps left, starting from state S, is something we can compute from this expected max tree on the right over here. That's exactly the equation we have over here. State S over here. We choose among actions available. Then for each action, there's a distribution over next states S prime. We'll be averaging over those next states S prime. And then there's a reward for the transition. And then there's gamma times the value when there are only k time steps left when we hit state S prime. We can initialize this with V0 equals 0 for all states. And then this actually has meaning. And we know that if we keep iterating this, we actually find V star. Assuming gamma is between 0 and 1. In fact, equal to 0 is fine too, but it's not a very interesting case because then you're done after one step. We also saw some intuition as to why this is true. We said, well, the difference between Vk of S and Vk plus 1 of S is as follows. For Vk of S, we solve a depth k expected max tree. Or maybe we don't solve that depth k expected max tree, but we do find the solution to that expected max tree by running value iteration. For Vk plus 1, we go one layer deeper. Then we consider what is the difference between those two. Well, first thing we do is we extend the tree for Vk by an extra layer. Make it k plus 1 deep, but set the reward equal to 0 everywhere over here. Now they're the same tree structures, with the only difference being the value or the reward associated with transitions happening in this last layer here. On the right, they're not necessarily 0. They're whatever they are for a state action state transition. On the left, they're set equal to 0. Now, if you look at the value at the top here and here, what's the influence of the rewards that are being given out in the bottom layer? Well, it's whatever those rewards are, they'll be averaged and so forth. But since they're at the bottom layer here, you'll have a discount of gamma to the k times whatever reward you're getting there. And that's the contribution you get at the top layer. Let's say the reward is bounded, then the contribution is bounded by the maximum of the absolute values of the reward times gamma to the k. Let's actually, here we know it's 0. Here we know it's bounded by gamma to the k max absolute value of r. As k goes to infinity, this quantity over here goes to 0. And hence, we show that as k goes to infinity, Vk and Vk plus 1 will approach each other. Something else you can understand from looking at this picture here. What would happen if I set V0 for states S equal to some random value? What will happen if I initialize value iteration this way? First question you might ask yourself, what's now the meaning of Vk? Right? The meaning of Vk will have changed. It's now what you would get if you were to act optimally in terms of expected sum of discounted rewards. And then in addition, if at the very end, when everything's over, if you were to hit state S, you get whatever you initialized V0S to be. So it's some kind of value you get at the end if you were to end in that particular state. So you can encode this if you wanted a finite horizon MDP, where at the end, certain states you might want to favor over other states, you could put that in V0 of S. How about if you keep going forever? You let k go to infinity. What's the contribution of V0? Well, V0 would be sitting over here, right? it'll actually be discounted by gamma to the k plus 1. So as long as you have a finite initialization of v0, which any reasonable thing would do, right? As you let k grow larger and larger and larger, the contribution of that initialization will disappear and will go down to 0. So what this shows, this intuition here, what I just said, shows that no matter how you initialize your v0s, if you run value iteration long enough, you will find v star. If you initialize it with 0, it's meaningful in that you get these vk values to have a particular meaning. If you initialize it randomly, they don't have a meaningful meaning. If you initialize it in some particular way where you say, well, I know where I want to be at the end, then it has that meaning. That's the value you get at the end. But in terms of just convergence, you can initialize this with anything you'd like. It'll still converge to v star. All right, any questions about value iteration and its convergence? Yes? Okay, we'll take it later. What I want to do now is look at a different way of solving the same types of problems. And we're going to look at policy specifically. And let's motivate this by looking at value iteration in action on our canonical example here. So we'll run this for 100 iterations. Let's take a look at what happens. Just look very carefully what's happening. And what I want you to look at is the arrows. Where are they pointing? And the arrows are what, based on the current depth, if you had this many steps left, where would you move or try to move? Look at whether they change or not. And at the same time, keep track of whether the values are changing or not. Okay, so we definitely understand that pattern that the values get non-zero first where the rewards are actually distributed, and it propagates from there. We see that the arrows, just one flip there, but that was it. Most of the time, nothing changes about the arrows where they're pointing. And the values have converged now too. But let's do this again and kind of keep track of how much the values change versus how much the arrows change. So what we see is that the values keep changing much longer than the arrows change, right? The values have converged. Here, after 14 iterations within 2 decimals of precision, values have converged. The direction of the arrows, so the actions, have converged too. But even before that, very little change in terms of what the preferred action was. Just at the bottom here, at some point, there was a flip when it realized that the path going around was actually slightly higher value than the path going off to the right. But everything else, pretty much the first time it got a non-zero value, it already got the right direction of action. If we look at value iteration, though, if we look at the algorithm we've been looking at, as you execute value iteration, you're always looping over all possible actions. And so the intuition from what we looked at there is that we're doing some spurious work here. Looping over all the actions might not be all that meaningful. Often it'll just be the case, whatever action we had at the previous iteration, when we went from k minus 1 to k, it's going to be the same action now. And that intuition is something we're going to go after in the next few slides and start to look at policies directly rather than just at values. All right, so first thing we have to do is to look at how to evaluate a policy. So we assume we're given a policy which looks something like this, maybe 2 policies, and the question is, which of the 2 is the better policy? Or more precisely, how valuable is each of these policies? Okay, so in standard expect the max, we had this over here, a choice over actions, and then a stochastic transition. When the policy pi is fixed, we lose the choice over actions. The action is fixed. Pi of s tells us what action to take. And then we still have the stochastic transition here. So by fixing the policy, we have a simpler expected max tree. You can imagine that the corresponding value iteration-like algorithm will be simpler than the one we've seen so far. The branching factor is smaller. We had A over here and just 1 over here in terms of branching. So it's a cheaper thing to compute. All right. So if we want to look at this in terms of recursive quantities, we now define V pi of S as the expected total discounted rewards starting in state S and following pi. This here used to say, when it was V star, it used to say n acting optimally. Now it says n following pi, and that's the same pi as on the top over here. All right, what would that be? Well, V pi of S, what do we get? We get a reward for being in state S, taking action pi of S, landing in state S prime. Then from then onwards, we get an expected sum of discounted rewards, and that's already something we have. That's V pi, that's the recursiveness here, V pi of S prime. Of course, we're one layer deeper in the tree, so we need to add a discount factor here, gamma. And then we don't know what's going to happen, so we sum over S prime, T, S, A, S prime, where actually A here is known to be pi of S. So that's our recursive equation. This is again a Bellman-like equation telling us how V pi of S is a function of, in fact, V pi of S itself. This is S prime, but this is sum over S prime, and if you stay in place, in fact, the same state S will appear again on the right. So it's a recursive characterization of V pi, which is a vector with S entries where S is the number of states. All right, this is same thing typeset. So let's look at an example. Let's say we have a simple MDP where you get to walk in this grid world, but once you land in a fire pit, dead, it gives you a very negative reward, and you might want to get across this bridge to the other side. Well, here's one example policy. Clearly not the optimal policy because it's always moving to the right, which would likely land you in the fire pit, but it's a policy. You could run policy evaluation to see, well, on the average, how much reward are you going to get? Here's another policy, go forward, which we'd expect to have a higher utility, but we haven't computed it yet. Here's what it actually looks like computed. Assuming you get a reward of 100 to make it across, when you make it across and you take the exit action there, that corresponds to the 100 over here. In the pits, it's minus 10. So the values there, no matter what policy you have, are minus 10 because you only have one action available. Every policy takes the same action. The interesting part is in the middle here. If you take the always go right or go east action, well, if you're up here, the expected sum of discounted rewards is 1.09. How do we get that? Well, 80% of the time you land over here. So that's a contribution of 0.8 times minus 10 times the discount factor. Once you go here, that's a 10% chance you get 100 times the discount factor times the 0.1, because that was the probability you'd go over there, and so forth. And so it averages out to 1.09. The further you are away from the other side of the bridge, the higher the chance that your jumping into the pit succeeds and that you get this very negative reward. Over here, 100 is of course best. Then when you're here, a reasonable chance of succeeding gets discounted, so you end up with an average of 70. But sometimes you'll land in the pits on the side. Over here it's lower. Why? Because you don't always succeed in moving up, and when you move off to the side, the reward is negative. And then same here, it's again a little lower. These are values of specific policies. This was the always go right policy. This was the always go up policy. There are many policies out there, right? We don't want to just enumerate all policies, evaluate them all, and then check which one is the best one, because the number of policies is, for each state, you get to choose an action, so it's the number of actions to the power number of states. So that's typically too many to try them all, but in principle, if you were to try them all, evaluate them all, you could see which one is best and just go with that one. Yes? Say it again? The way we think of it is that if you intend to go in a certain direction, that's your action choice, your intended direction, but then the consequence could be that you move in a different direction. Yes, absolutely. We can rethink this, right? We can say, what would the values be in a different MDP where there's no such stochasticity? If there were no such stochasticity and actions were deterministic, then the value of this state over here would be gamma times 100. Because the immediate reward would be 0, but then at the next time we'd get the 100 reward. It would be discounted because it was one time step later. If it was deterministic, then this one would have gamma squared times 100, and this one would have gamma to the third times 100. Because it's not deterministic, it's more complicated because you move off to the sides and it's a more complicated computation. All right, so how do we compute the values for each state for a given fixed policy? All right, we can do the same thing we did for value iteration. In some sense, this is a simplified version. You can think of this as now being in a new MDP where the actions available to you in each state are limited to just one action. And in that new MDP, running value iteration will give you the value of that policy. But when you're maxing over all actions, since there's only one action, you can just leave out the max over all actions. So it's kind of a slimmed down version of what we already did. You can do these recursive updates. You start with 0 time steps left. Value of the policy for each state is 0. And then this is value iteration, but without the max over here. Why is the max gone? Because you don't get to choose the action. Otherwise, this is exactly the same as the value iteration updates. You can do something else. If you look at these equations here, once they would be satisfied, right? Remember we said what we're doing is really solving a nonlinear system of equations when we run value iteration. It's just one way of solving that system. What about this? We have S equations, if there are S states, right? Number of states is equal to the number of equations. Number of variables equals to the number of states. There's a value for each state. And when we have converged, at convergence, this will be true with equality. And we know this will converge. How do we know this will converge? We can show this in two ways, right? One way to show it is to go through the same proof sketch as we did for value iteration. Another way to show it is to say, this is value iteration, just in a special MDP where every state has only one action available, and we know value iteration converges. So we know this converges. At convergence, this holds true with equality. Let's take a look at this. What are the variables in this equation? This is a variable, and this is a variable. T is a given. That's part of what you get when you get the MDP. That's a table, three-dimensional table. It's not a variable. It's not something you try to solve for. R, same thing there. It's something that's given. It's a constant when you're doing these operations. So if you look at this carefully, this is actually a linear equation relating these quantities. There's nothing nonlinear in there. By taking out the max, the nonlinearity is gone. Let's go back 2 slides here to spell it out a little more explicitly. This is the linear equation that we're trying to, linear set of equations, because there's one for each state, that we're trying to solve right now. Variables are v pi of s. For each state s, s prime is one of those states. And that's it. Left side, linear, is just an occurrence of the variable. On the right side, the only place the variable appears is over here. It's multiplied by gamma. That's a linear operation because gamma is a constant. Then after that, it's multiplied by t, which is some number we look up in a table, right, for each s pi s s prime. And then there's a summation. So we have a linear combination of the variables on the right-hand side and just the variables on the left-hand side of these equations. This means we have a linear system of equations. You don't need value iteration to solve this. You can solve this with any system that you have available to you to solve a linear system of equations. Maybe some kind of Gaussian elimination, maybe a Cholesky decomposition, whatever is your favorite way of solving linear systems of equations. You can apply that and find a solution to this set of equations, and that gives you the values of a fixed policy. What's the efficiency of the top thing here? Well, now we have order s squared per iteration. Contrast with value iteration at order s squared a, because we need to loop over all actions in each update. So we reduce the complexity. Of course, we're not finding the same thing. We're now finding the value of a specific policy that's fixed. We're now finding the optimal value. Solving linear systems of equations can be done in a finite amount of time, which is nice. Here, in principle, to get the exact solution, with this approach, you would be running this infinitely long, right? Because this is a series. You go till k equals infinity, and k reaching infinity can take infinitely long. We know in practice, we only need to run up to machine precision at best, so it's not infinitely long. But so we now have a different way of finding values that, even theoretically speaking, doesn't take infinitely long. We know theoretically speaking, this takes a finite amount of time, solving a linear system of equations. So we can choose. We have now two methods to perform policy evaluation. All right. Next thing we're going to look at is policy extraction. Then we're going to combine policy evaluation and policy extraction to get a new algorithm to solve MDPs. So what's policy extraction? The idea here is that you somehow come up with a policy from something. So let's imagine you have the optimal values V star available to you. And I tell you, well, you're in this state over here. Your value is 0.95. What are you going to do? Just knowing that value is not enough to know what you should do. To know what to do, you actually need to know something else. You need to know the value for each of the actions available in that state. If you have the Q values, you could just look up which action is the highest Q value for that state and take that action. If you just have the values, that's not enough in and of itself. So the way we extract an action given values is as follows. We say, well, we need to consider all actions, so we'll max over all actions. How good is an action? Well, for a given state, we don't know where we're going to go, so we sum over all next state S prime. Average over those next states what the values of those next states, which is R S A S prime plus gamma V star of S prime. The action that achieves this maximum we call the argmax, right? The thing that achieves the maximum is the argmax. That's the way to act optimally. So if you're given a set of values, this operation here is extracting what people call the one-step look-ahead policy relative to that set of values, and that's the way to get the optimal action out. The one-step look-ahead relative to the optimal values V star gives you the optimal action A. Sorry, the optimal action pi star for that state S.
You mentioned earlier that to solve the linear system of Bellman equations, we use an calculator for one MATLAB. That implies that in order to use factor values, data game beforehand.
That's a good point. So far we've assumed that T and R and gamma are given to us. In the next two lectures, we'll start looking at what happens when they're not given to us, and we'll start looking at what happens when maybe the state space is so large that you can't assume they're just available as a table, and you can't assume that you can just loop over them and look at all of them. But for now, we assume that they're given, and we assume the state space and the action space are small enough we can loop over all of them. And we'll see that when we can't do that, the algorithms we come up with then will be based on the one we're seeing now. In fact, you can do it based on value iteration or based on the one we're building up to now. But either way, you want to start from what we have now to tackle those more difficult cases. But absolutely, we'll want to tackle those more difficult cases. But just a little bit of patience for those.
So in other words, yes, problems, but we're just not quite realistic yet.
Say that again?
In other words, yes, that's a bit of a problem. It might have spaces.
In practice, you're pretty much guaranteed to have the problem that your state space will be too large, because if you just think of the state spaces we saw in the first few lectures, right? Just a simple Pac-Man game, right? 2 ghosts, Pac-Man, food pellets, state space is huge, right? And that's pretty simple. Let alone you want a robot to do something in the real world where things could be a lot more complicated. You're guaranteed that your state space is too large to run any of these algorithms the way we've seen it right here, right now. But they do form the foundation for what we'll do later, and that's why it's important we look at it now in this scenario, and later we'll see how to handle the realistic scenarios. All right, so this is a typeset version of what we just looked at. This is the way to extract the optimal action, assuming you have the optimal values. All right, so that's policy extraction. We've seen 2 things now. We've seen policy extraction and policy evaluation. Policy extraction, of course, is very simple if you have Q values, because the Q values tell you exactly what the right action is. You just look up, let's say you're here again, what's the right action? Well, 0.95 is the highest of the 4 Q values, so going east is the optimal action there. All right, that's our equation here. In the future lectures, we'll see that often we'll end up keeping around Q values rather than V values, but it depends on the scenario what you might want to keep around. Okay, let's take a short break here, and after the break, let's look at how we can combine policy extraction and policy evaluation to get policy iteration, which is a new approach to find the optimal policy. All right, let's restart. Any questions about the first half of lecture? Nope. Over there.
Could you just clarify what the difference is between the Q states and V states?
Okay, what's the difference between Q states and V states? Let's go to an expected max tree here. All right. So this is a piece of terminology, right? It's a definition. And when we talk about V states, values, it refers to the actual states. It's these kind of states. The state your agent actually could be in. The Q states are not real states in the same sense. They're not states in your state space. They're a computational mechanism that we use, or computational terminology that we use to refer to the chance nodes here. Once in this expected max tree, you're in a chance node. We'll say you're in a Q state. It's a state of the game or of the MDP where you committed to an action, but the action hasn't played out yet. So you're committed to the pious action in this case, but stochastic transition still has to play out for you. So Q states are over here, and the V states are over here. Right?
So is there no way to, I mean, so Q states are required if you have a stochastic node in your MDP?
Another way to put it, what you're saying, but maybe the way I'd put it is that once you have an expected max tree like this, if we want to name these nodes differently, one way to name them is to call them the chance nodes, but that doesn't relate it back to what we're computing. We're computing these V values and these Q values. If we call them Q states, that's an easier mnemonic to recall what values correspond to them, right? So you can just as well call this a chance node or a Q state. When you say chance node, sure, it emphasizes this aspect over here. When you say Q state, it emphasizes the fact that the value associated with this node will be a Q value.
So it just refers to the concept of...
Correct. Yes?
So I mean, basically V is realized, like realized score, whatever you're going for, and Q is just a possibility.
V is indeed the expected utility if you act optimally from your current state. Whereas a Q value is if at the first time step you do whatever you did, whatever A says it is, and from then onwards act optimally. So that's just what they are. I don't think you should look into deeper meaning than just that, but at the same time it's important to precisely know that's what they are. One of them act optimally always from the beginning, the other one you get one action to choose initially, and from then onwards you act optimally. All right, policy iteration. This is going to be a new approach to solving MDPs. Note that in principle we already have seen two approaches, right? We can solve an MDP using value iteration. We saw that in last lecture, reviewed it this lecture. In principle, if it's a finite horizon MDP, right, you can then solve it with expected max. You might do a lot of repeated computation, but that's another way to find the values in an MDP. So we've seen two ways to solving them so far. The preferred way so far, value iteration. Now we'll see something that's on par with value iteration called policy iteration. It's a little different, but it gives us the optimal values also. So let's go back to that demo we looked at here and remind ourselves of what we're looking at here. What we're looking at is that the values propagate out, indeed, they change, and they keep changing for a while, but the policy is fixed pretty quickly, pretty early on. And so the question is, can you do something that more directly zones in on the policy and maybe knows when you're done? You say, hey, I found the optimal policy. No need to keep running updates and updates. All right, so the problem with value iteration is that you keep repeating these updates, and quite often, this max over A is kind of spurious because, well, it's going to be the same action that you found in the previous iteration. So you do a lot of work per iteration. Is factor A more expensive compared to if you had fixed the action? So the second problem, aside from it being expensive in that sense, is that, so it's expensive, so you do extra work. Second problem is that the policy is often done before the values are done. But value iteration is not telling you that, right? It's not saying, hey, the policy will never change anymore. It's just saying, hey, I'm still updating my values. Who knows, maybe at some point the policy will change. And in fact, we saw one particular node, right, where it changed pretty late. And we understand why, right? We know for this node over here, it's going to change pretty late. Why is that? Because at first, when it gets a non-zero value, it comes from the shortest path to a non-zero reward that's positive. But then later it realizes, after more updates, that there's this longer path. And even initially when that longer path exists, it doesn't take it yet because these values here aren't converged yet. They're still lower than they're going to be. But once these values are converged to the left of it, it will get a higher value by going to the left and it'll switch over. Right? So we see some values still change pretty late in the game, and we don't really have any idea of whether, some policy entries will still change, and we don't know whether that's going to happen or not. All right, so this is just a summary on the slides for you because you don't have that demo available, though in principle you could build it from your project 3. So let's now look at an alternative approach for finding optimal values. Step 1, you do policy evaluation. So you assume there's a policy given to you. Maybe you pick a random policy. You pick something and evaluate the value of that policy for each state. We know how to do that. You could either run this something that looks like value iteration, right, but without the max over actions till convergence, or you could solve a linear system of equations. It takes a finite amount of time, find the value of each state under that policy. Once you've found the value of each state under that policy, you update the policy using the policy extraction approach that we've looked at. You'll do policy extraction, but with the values you just found. It won't be the optimal values, so you don't necessarily find the optimal policy here, but with the values you just found, you do policy extraction, which is doing a one-step look ahead, see what is the best action under the current values. Then you repeat those steps until policy converges. So this is a loop here. What are the properties of this? First of all, what's happening? When you run policy evaluation, you solve for values of a policy. That's a lot like value iteration or solving a system of equations. Then you improve the policy. And I've called it improving, but I haven't said to you why this is improving. And then you repeat. So one property is that if you keep doing this till it's converged, it actually will have found the optimal values in the optimal policy. First piece of intuition I want to give you is here. Step 2, policy improvement. Why is doing this one-step look ahead, policy extraction, an improvement of the policy? We haven't said anything about that. Let's take a look at the equations and think about what that really does, right? So this thing we know, that's one way of solving for the value of a policy. But this thing here, we've only seen so far with V star over here. With V star over there, we know that is exactly what we need to do to find the optimal action. Here we have a V of some different policy, pi I. Why can we call this improvement? Well, here's the intuition. If you were to always act according to the policy pi I, you would get the value V pi I of S prime from state S prime onwards, right, on expectation. Now, if at the current time, instead of just blindly following the policy pi I, you say, well, at the current time, what I'm going to do, I'm going to look at all my options, check what the expected utility would be if I first take action A, followed by then always executing according to the policy pi I. Now look over all actions, see which one is best. Then I know that it's better to then take that best action, followed by the policy pi I, than just blindly follow the policy pi I already from the first step. Because now I'm picking the best one among all actions, followed by pi I, rather than fixing at the first time and then pi I. So doing this thing where at the first time you do something better, followed by sticking to your plan, pi I, is better than at the first time just sticking to your plan already. Now, what does this policy pi I plus 1 actually do? After you then executed that first action, wherever you land, you would repeat this procedure. It would say, hey, rather than sticking to the policy pi I, which I initially promised to do and I know what the value was going to be, I can do better. I can at first change my mind based on whatever looks best, based on this one-step look ahead, and from then onwards sticking with pi I. And so you can repeat this reasoning process and you see that policy pi I plus 1 is guaranteed to perform better than the policy pi I, because at every step, you're actually doing something that's better than just blindly following pi I. Okay, so that's one intuition I want you to get here, is that this is indeed policy improvement. You might say, well, what happens if for every state, the pick I make here gives me back the same as pi I of S? So pi I plus 1 equals pi I. That means you reach convergence. And what's interesting about that, once you reached convergence, if pi I equals pi I plus 1, let's take a look at what actually happened here. The values we found satisfy this equation over here. Down here, we look at the same equation, but with a max. If pi I plus 1 equals pi I, what that means is that choosing the max is the same as sticking to pi I, which means that the values we found up here actually also satisfy this equation with the max up here, because the max would coincide with pi I of S. Which means that once pi I and pi I plus 1 are the same, the values we found are V star. Well, if the value of a policy pi I for each state is equal to V star, then that means that policy pi I is the optimal or one of the optimal policies because it achieves maximum expected utility. So we now know that once we have converged here, we actually have found the optimal policy and the optimal values. Are we guaranteed to converge here? How long can this take? Well, if you look at this equation over here, we said if it's the same, we're done, right? We found the optimal policy and optimal values. If it's not the same, then it's improving the values. Well, how many times can we improve the values until we must be done, right? You improve the values again, improve them again as you loop through this, right? How often can that repeat? Well, the number of policies that exist for an MDP with a finite number of states, finite number of actions to the power number of states. So after you've gone through this cycle this many times, you must have converged, because you can never encounter the same thing again. If you encounter the same thing again, that means you have converged, right? You can't see a policy 1, then a 2, then policy 3, and so forth, and then all of a sudden come back to 1, because you know you've been improving, and that last step must be an improvement too. That means you cannot go back to something worse. So because you always improve, once you've seen a policy, you've improved from it, moved away from it, you can never get back to it. And so at most, after this many iterations through this outer loop, we have found the optimal policy and the optimal values. Actually, I'm gonna, since with the time we have left, I'm gonna postpone questions till after lecture. Then, otherwise we might not get till the end. All right, so that's policy iteration. So both value iteration and policy iteration are valid approaches to find the optimal value function and the optimal policy accordingly. In value iteration, every iteration updates both the values and implicitly the policy, because you're doing that max over actions. Implicitly, you're finding a new policy. You're not storing it, not explicitly interleaving policy and values. You're doing it all at once. But in some sense, you're finding updates for both. Policy iteration, you alternate between updates for value and updates for the policy. There are also many variants that we're not getting into the details for, but in principle, you can do variants here where instead of doing this till convergence, which is the standard thing to do, or solve the linear set of equations, instead of doing this, you might say, well, I'm just going to do a couple of updates over there. And after I update every state twice here, the value of every state twice here, I do a policy update, and then I go back here and so forth. That's something between value iteration and policy iteration, and often those are some of the fastest methods. Because remember, the intuition here is that we said often the action will stay the same. And so for a couple of updates, using the same action might be fine. Then you do an update to your action. Then you do a couple of updates to the value and so forth. So those are kind of mixed methods. They have guarantees too. If you consider every state infinitely often for value update and action update, then these mixed methods will converge too, and to the right thing. So we have two MDP-specific solution methods now. Let's summarize and then start thinking about what happens if we have less knowledge about the MDP. So we compute optimal values. Let's say you want to compute optimal values. You can use value iteration or policy iteration. If the policy is fixed and given to you, you use policy evaluation, which remember, you could do in two ways. Solving a linear system of equations by just calling some linear system solver, or by running something like value iteration, but without the max for the fixed policy. If you need to turn values into a policy, you do this one-step look-ahead thing, which if you have the optimal values, will give you the optimal policy. If you have non-optimal values, you'll have the value, if you were to take that action, followed by following whatever policy that gave you that future value. They all look the same. Well, they basically are the same. There's a lot of similarity between them, and it's important to understand, yes, indeed, they look the same, but there are subtle differences. And you'll see, for example, in your next homework and exams will ask you, what is the right update equation for this variant, where we change the definition of an MDP, where now things are a little different in this or this way, and we'll throw variants at you with maxes and summations all over the place. And it's important that you understand where they're supposed to appear and what they exactly mean. All right, so now let's switch gears and look at something different that will build up to the next two lectures. We'll be entering, or our CS188 robot will enter the 188 casino. And it's a very nice casino in that if you play this slot machine, you always get $1. Who doesn't want to go there? And the red slot machine sometimes gives you $2, sometimes gives you nothing. All right, we can model this as an MDP as follows. We have two actions available, playing the blue machine or the red machine. We have two states. The reason we have two states here is an artifact of the way we define MDPs. Sometimes in MDPs it's allowed to have a reward that's non-deterministic. We have a deterministic reward for a fixed state action, next state, the reward is fixed. So if we want a stochastic consequence in terms of just reward, we need to encode it by having an extra state. So if we lost playing the red machine, the red bandit, then we land in the lose state. If we win, we land in the win state. Once we landed in such state, we have both actions available to us. There is nothing really different. The reason there's two states is not because of the transitions here, but just because of the rewards. So let's look at this. If we are in the win state, we take the blue bandit action, we win a reward of $1, and this is with probability 1. If we just lost, same thing, we take the blue action, we get a reward of 1, guaranteed. If we just won or lost, either way, we take the red action with probability 0.75, we win $2, no matter where we started. And with probability 0.25, we win $0. All right, let's say we get to play for 100 time steps. What is the right thing to do here? What's the optimal policy?
Play red.
I'm hearing playing red. Why is that? Because the way we define optimal, right, will give you on the average the highest payoff. Play red will give you on the average 150. Play blue will give you 100. 150 is higher than 100, so that's what we prefer. All right, so that's the same thing, typeset. The important thing I want to emphasize right now is what we've done so far is something called offline planning. What I mean with that is that we came to this conclusion of red being the right thing without ever actually playing the game. We never played the game. We just looked at the definition of the MDP. We said red is the right thing. That's it, and that's what we'll play. Then when we start playing, after we plan, we start playing, and we just see what happens. Now it's stochastic, of course. We don't know what happens. We know red is the right thing to do, so we'd go with red. We're lucky, we get $2. Red again, lucky again. Less lucky this time around. Does that mean we should switch to blue? No, we made a plan. We found the optimal plan. The optimal plan is to always play red. So we keep going no matter what happens because we know that's the right thing to do. Even after this unlucky streak at the end, we know that's still the right thing to do. After 10 actions, what we get, we got a total of 12. On the average, with a 0.75 chance of winning, we would win $2. Our expectation was to get 15. This means we had an unlucky run. That's just the way it is, right? On expectation, we get something, and in reality, we always get something that's kind of random. If we play often enough, it'll match up. All right, now let's change the nature of the game, and let's just put a question mark on these transitions here. What does that mean? That means that we now don't know the probability of winning. When we play the red bandit, the red slot machine, we don't know what the probabilities of winning or losing. So we're now still faced with an MDP. There is still an MDP. We know most about the MDP, but we don't know the probability of winning or losing when we're in the red, when we pull the red bandit's lever. All right, so let's play again. What should we do now? Suggestion over there.
You should play red 10 and 20 times to figure out what its chance is, and then if it's less than blue, play blue.
Okay, so the suggestion here was, since we don't know what's going on with red, play it 10 to 20 times. See how it plays, see what happens, compare it to what you know you're guaranteed to get from blue, and after 10 or 20 times, you make up your mind. You say, well, on the average I got more than 1, so that's a good thing, I'm going to keep playing red, or on the average I got less than 1, I should switch to blue because that's going to be better. So this is something very different from what we've done so far. Yes?
Would it be possible to, I don't know if I understand correctly, but I mean, wouldn't that be like finding the, figuring out the game and then playing it still in a way? I mean, would it be possible possible to figure out the model as you play, like with the reward?
Exactly. So the intuition here is that as you do this, as you play 10 or 20 times on the red machine, and then maybe change your mind, you are figuring out what the parameters of the MDP are. You can say, well, after maybe, let's say 100 times, which gives us maybe a good estimate, maybe after playing 100 times, 80% of the time I got the payoff of $2, 20% not. Maybe I now posit that that's the parameters of my MDP. I solve the MDP based on those parameters and act optimally with respect to my estimate of the MDP. But key here is that it's still only an estimate, and you're still left with a question like, was pulling it 100 times enough? Maybe it was a lucky streak, maybe an unlucky streak. So you probably don't want to stop. You probably want to keep, as long as you play red, you want to keep track of, well, where am I at? Is it time to switch or not? The unfortunate thing about blue is once you switch, you get no information anymore about red. So once you switch, you're kind of just playing blue, and there's nothing that will change your mind, right? All right, so let's say you play and get 0, 0, 0, 2, 0, 2, 0, 0, 0, 0. What will you do? Well, it depends on the context. Let's say you got to pull this machine 100 more times, right? Any of the machines. Then maybe you'd say, well, I'm going to take my chance and check red a little longer. If you only had 5 more times to pull a machine, you'd probably switch to blue because it's looking pretty bad and 5 is not enough to find out more. So what just happened? We just switched from what is planning to learning. Now, as you act, you build up experience about how the environment works, and you're going to try to use that experience to do better. It's still an MDP, but you have to learn about the MDP by acting in it. This opens up a whole range of new challenges. The first one is exploration. So that's the one everybody kind of right away started thinking about is you need to take actions that allow you to understand how the system works. So information gathering becomes part of the game now. You take actions not to get reward per se, but to collect information about the MDP. Exploitation. At some point, you want to say, well, it's been enough information gathering. I should really get actual rewards at some point. So you'll have to trade that off. Should I do more exploration or should I start exploiting? Then a new concept called regret. You could say, well, I took a sequence of actions. Let's say I got to act for 100 time steps. How much reward did I get? And how much reward would have been achieved by the optimal policy on expectation? You can take the difference. That difference tells you something about how well you were acting. You have to look at concepts of sampling, right? You don't get to see the expected values of anything. You just get to see a sample value. From sample values, you can estimate the expected values and the probabilities. But now you need to think about, well, how accurately am I estimating those? How many samples do I need to get good estimates? A lot of new challenges open up. And one thing to realize here is that all I changed, going from the original MDP that we had, which is the one over here, right, we had this MDP, which is a tiny, tiny MDP, and all we did was put question marks on these transition probabilities here. Just one number. We said we don't know, and all of a sudden there's this whole host of new challenges that we need to think about. That's what we're going to look at the next 2 lectures. That's it for today.